Hey guys, today we're going to be talking about DNA replication, which is copying the DNA. Now remember, this occurs in interphase in the S phase. Now way back when in the 50s, they weren't exactly sure how this was done, so they had three ideas. Was it conservative replication, where the parent strands were conserved completely and we just built a whole new strand? Was it semi-conservative replication, where the parent strands split and were used as templates to create the new strands on? Or was it dispersive replication, where pieces of the old and pieces of the new were intermixed? Well, Mendelssohn and Stahl in 57 labeled the parent strand with heavy nitrogen. This is much heavier nitrogen 15 than nitrogen 14, so they could actually track the parent strand. Now, when they did this, they found that the nitrogen 15 was in one strand of the replicated DNA, and the nitrogen 14 was in the other half of the strand, so that they determined that replication was done semi-conservatively, or partly conserved. So here are some big key features of the process of replication. The double strand does have to unwind. When it unwinds, it creates a replication fork. New strands have the pairing of complementary bases added on to them. Two molecules are made. Each one has one old and one new strand. This is semi-conservative replication. And the two sister chromatids are made during this S phase. So the overview again. The parent strand here, it has to separate and unwind. New complementary bases are added on, and the sugar phosphate backbones have to be connected to create two new strands. Now this is a great chart that gives you all the key players of replication. DNA helicase unwinds the double helix. Gyrase relieves the tension or keeps it from supercoiling. The single-stranded binding proteins do exactly what they say. They bind to the single strand to protect them and keep them from re-annealing or reattaching. We have short RNA primers, which are a little piece of RNA in which the DNA can be added onto. Primase is the one that lays down these short segments of RNA. DNA polymerase, which adds complementary DNA to the strands. Exonuclease, exo meaning take out, nuclease meaning nucleotide, will remove those RNA primers because we don't want RNA just sitting around in our DNA, and will lay down complementary DNA in place to fill those gaps. Our Okazaki fragments are short segments of the DNA that are created on the lagging strands that we'll see in a moment. And then ligase is the enzyme that connects the sugar phosphate backbones, creating the full new strain. So let's see how these guys actually play. Replication. So we have helicase here that actually unzips or breaks the hydrogen bond between the DNA strands, separating them. Remember, gyrase relaxes the DNA to prevent supercoiling. Single-stranded binding proteins bind to protect the single strand and keep them apart. And primase here lays down a short strip of RNA primer so that DNA can be added onto it. Supercoiling is what we see here. When you open up a coiled strand, it puts tension on the other side. Gyrase prevents this tension and keeps it nice so that the helicase can open it up nicely. So, now that we have the open replication fork, we have our primers. DNA polymerase can add to the 3' end of our primer. Now that's fine on the leading strands, but on the lagging strand we've got a problem, because if we add to the 3' end, this guy just ends up falling off right here. That's a problem. And we're going to see what happens. The leading strand can go continuous, just add more and more complementary DNA as long as that DNA helicase continues to unzip the DNA. But here we end up with Okazaki fragments. The primase has to continuously lay down little strips of primer as the DNA is exposed or unwound. Polymerase jumps back to the primers and adds another small segment of DNA called an Okazaki fragment. It will continue until it hits the primer in front of it, and then bounce backwards to the next primer and add more and bounce and continue. Again, this is a discontinuous strand. The exonucleases come behind and take out those RNA primers and add in complementary DNA to add in and fill in those gaps, and ligase connects the sugar phosphate backbone. Again, this is a great chart. If you did not copy it down earlier, it gives you all the enzymes of all the key players and all their functions. And here's a really good picture that shows you all the different pieces. Helicase here, gyrase behind it. We've got primase laying down these RNA primers. We have DNA polymerase adding to the 3' end, adding complementary DNA. We have exonuclease removing those primers, and then ligase coming and connecting those sugar phosphate backbones.
When DNA replicates, its strands are separated by the enzyme helicase. Single-stranded DNA binding proteins keep the strands from reannealing. One DNA strand encodes the leading strand, which forms from its 5' to its 3' end, using DNA polymerase III. No problem here, but the lagging strand presents problems. It has to form from 5' to 3' too. It forms in pieces called Okazaki fragments. First, an RNA primase lays down an RNA primer. Then, DNA polymerase III lays down new DNA. The process repeats again and again. DNA polymerase I replaces the RNA primers with DNA. Finally, DNA ligase links the Okazaki fragments.
Well, hey ligase, what you been up to? Just making ends meet. That's all I got for you today.